These are 13 of the most extreme objects and events astronomers have ever confirmed in the universe, and every single one of them would end life on Earth instantly if it happened to be in the wrong place at the wrong time. If you've ever wondered what terrifying actually looks like once you strip away the movie special effects and just look at what telescopes have genuinely measured, stick around, because these numbers are real, they're documented, and some of them are close enough to home that they should probably worry you a little. Before we get into it, go ahead and hit that subscribe button and tap the like. It genuinely helps this channel keep making videos like this one. And now, let's get into the objects themselves. We're going to start close to home, in a cosmic sense anyway, with something sitting right at the center of our own galaxy. Every galaxy, as far as astronomers can tell, has a supermassive black hole anchoring its middle, and ours is called Sagittarius A star. It's roughly 27,000 light-years from Earth, which sounds distant until you remember the Milky Way itself is over 100,000 light-years across, and that makes Sagittarius A star practically a next-door neighbor by galactic standards. Its mass comes out to about 4 million times the mass of our Sun, all of it packed into a region so small and so dense that light itself can't escape once it crosses the boundary. That boundary is what astronomers call the event horizon, and it isn't a physical surface. There's nothing solid to touch. It's simply the point of no return, the line at which the gravity pulling inward becomes so extreme that not even light, the fastest thing in existence, has enough speed to break free again. Cross it, and whatever you are, you're not coming back out, and you're not sending any information back out either, which is part of why black holes are so genuinely hard to study. Whatever happens on the other side of that line simply stays a mystery. The idea of an object like this isn't new either, which might surprise you. Back in 1783, an English clergyman and scientist named John Mickle proposed to the Royal Society the idea of a star so massive and so dense that its own escape velocity would exceed the speed of light, meaning light itself couldn't get away from it, and the star would effectively be invisible, detectable only by how its gravity yanked around any companion star nearby. The idea was mostly forgotten for over a century, until 1915 and 1916, when Albert Einstein published his general theory of relativity, and a physicist named Karl Schwarzschild used Einstein's own equations to describe exactly this kind of object mathematically, a region where space-time warps in on itself so completely that light can't climb back out. It took until 1967 for physicist John Archibald Wheeler to give the concept the name we use today, black hole. And it took until 2019, more than 2 centuries after Michel's original idea, for humanity to actually photograph one. For decades, astronomers knew Sagittarius A star was there only because of how it affected the stars orbiting around it, stars getting flung around at incredible speeds by something massive and invisible, tracing out orbits that only made sense if an object with millions of times the Sun's mass was sitting at the center, completely dark. Nobody had actually seen it directly, not until May 12, 2022. That's the day the Event Horizon Telescope collaboration released the first ever image of our galaxy's black hole, and it showed exactly what physics predicted: a glowing, slightly uneven ring of light wrapped around a dark, empty center, the shadow cast by the black hole itself. That glowing ring isn't the black hole, it's superheated gas, swirling just outside the event horizon, gas being stretched and accelerated to a meaningful fraction of the speed of light before it finally crosses over and disappears forever. And the dark patch in the middle is simply the silhouette the black hole casts against that glow. Getting that image took an enormous coordinated effort. The Event Horizon Telescope isn't one telescope, it's 8 radio observatories scattered across the planet, all linked together electronically to behave like a single telescope the size of Earth, because you need an instrument that large to resolve something as small, from our distance, as a black hole's shadow. And here's the part that surprised even the scientists working on it. 3 years earlier, in 2019, that same collaboration had already managed to photograph a black hole in a completely different galaxy, one called M87, sitting far, far farther away than our own galactic center. You'd think the closer black hole would be the easier one to photograph, but it wasn't, and the reason comes down to size. M87's black hole weighs in at around 6.5 billion solar masses, so much larger than Sagittarius A star that gas swirling around it takes days or even weeks to complete a single orbit, giving the image time to hold still while astronomers captured it. Sagittarius A star, despite being the closer target, is so much smaller that gas around it completes a full orbit in a matter of minutes. As Event Horizon Telescope scientist Chi-Kwan Chan put it, the innermost orbit around Sagittarius A star takes roughly 30 minutes, compared to about 30 days for M87's black hole, and that meant the source was flickering and reshaping itself even while the telescopes were staring right at it. The data behind that famous 2022 image was actually recorded back in April of 2017, and it took the team roughly 5 years just to process it into something recognizable, meaning the picture the world finally saw was, in a strange way, already 5 years old the moment it was published. Here's where Sagittarius A star gets genuinely frightening, because this isn't just an object sitting quietly in the middle of our galaxy, it's an object that has, at least once, reached out and thrown a star clean across the galaxy like a slingshot. In 2019, astronomer Sergei Kopasov of Carnegie Mellon University and his team, working with something called the Southern Stellar Stream Spectroscopic Survey, identified a star now known as S5HVS1. This star sits in the constellation Grus, about 29,000 light-years from Earth, and it's moving at roughly 1,755 kilometers per second, nearly 4 million miles an hour. When the team traced its path backward through time, the trajectory pointed directly at the galactic center, at Sagittarius A star itself. The best explanation is that S5HVS1 used to be part of a binary system, two stars locked in orbit around each other, and when that pair wandered too close to the black hole's gravity ripped them apart. This is what's called the Hills mechanism, a process first proposed theoretically back in 1988, decades before anyone actually confirmed it happening. When a tightly bound pair of stars passes close enough to a black hole, the black hole's gravity acts unevenly on the two of them, and one gets captured into a tight orbit, sometimes swallowed entirely, while its partner gets whipped away at a dramatically higher speed than either star started with, essentially borrowing energy from the black hole's own gravity well, the way a slingshot borrows momentum from a planet. In this case, one star got captured and pulled in. The other, S5HVS1, got flung outward at an estimated ejection speed of around 1,800 kilometers per second, and it's been traveling ever since, for close to 4.8 million years, on a path that will eventually carry it completely out of the Milky Way and into the emptiness of intergalactic space. Sergei Kopasov summed up why this discovery mattered so much. "This is super exciting," he said, "as we have long suspected that black holes can eject stars with very high velocities. However, we never had an unambiguous association of such a fast star with the galactic center." In other words, astronomers had guessed for decades that something like this could happen, but this was the first time they could point at a specific star and say, with confidence, a black hole did this. One of the researchers on the project put it in more human terms too, noting the star was born in one of the most extreme environments in the galaxy, right next to a supermassive black hole, surrounded by other stars, and now it's leaving all of that behind entirely, destined to travel alone through empty space for the rest of its existence, and eventually to die completely alone outside the galaxy that made it. A black hole flinging a whole star out of the galaxy is one kind of violence. Tearing a star apart entirely is another, and astronomers have actually watched that happen too. It's called a tidal disruption event, and one of the clearest examples ever recorded is something called Assassin 14 Li, discovered in November 2014 by a ground-based survey called the All-Sky Automated Survey for Supernovae, sitting inside a galaxy called PGC 43234, about 290 million light-years from Earth. At the time of its discovery, it was the closest event of its kind found in about a decade, which gave scientists an unusually detailed look at what actually happens when a star gets too close to a black hole. The mechanics are almost sickeningly simple. A black hole's gravity pulls dramatically harder on the near side of a passing star than it does on the far side, and that difference in pull, called a tidal force, the same basic force that raises the ocean tides on Earth, just at an almost incomprehensibly larger scale, is enough to physically shred the star apart, stretching it into a long, thin stream of gas before it's even fully torn loose. Roughly half the wreckage gets pulled into the black hole, heating up violently and producing a bright flare across optical, ultraviolet, and X-ray light, while the other half gets flung outward into space as an outflowing wind. Later analysis using NASA's Chandra X-ray Observatory and Europe's XMM Newton, led by John Miller of the University of Michigan, estimated the shredded star weighed roughly 3 times the mass of our own Sun, making it one of the largest stars ever confirmed destroyed this way. Miller summed up the value of studying an event like this simply, saying, "We have seen evidence for a handful of tidal disruptions over the years and have developed a lot of ideas of what goes on." Researcher Brenna Mockler, who worked on later analysis of the same event, put it even more bluntly, calling the X-ray telescopes used to study it forensic tools in space, because that's essentially what astronomers were doing, examining the debris field of a murdered star to figure out exactly what it used to be. That's terrifying enough on its own, a black hole with enough gravitational violence to fling a star out of the galaxy or shred one apart entirely. But Sagittarius A star, at 4 million solar masses, is relatively speaking one of the smaller monsters out there. So let's go bigger, much, much bigger, and travel about 10.8 billion light-years away to something called TON 618. TON 618 was first noticed in 1957 in a survey of faint blue objects conducted at the Tonantzintla Observatory in Mexico by astronomers Braulio Iriarte and Enrique Chavira. At the time, nobody knew what they were looking at. The concept of a quasar hadn't even been defined yet. That wouldn't happen until 1963. So this strange, faint point of light just got filed away as catalogue entry number 618, which is where the name comes from. It wasn't until 1970 when astronomers detected radio emissions coming from it, and it was later confirmed through spectral analysis by Marie-Hélène Ulrich at the McDonald Observatory in Texas that TON 618 was identified for what it really is, a quasar, which is really just the name astronomers give to the blazing, energy-spewing core of a distant galaxy, powered by a black hole feeding on enormous quantities of gas and matter. What we're actually seeing when we look at a quasar isn't the black hole itself. Black holes, by definition, don't glow. What we're seeing is the accretion disk, a swirling, superheated whirlpool of infalling gas that gets compressed and friction heated to millions of degrees before it finally crosses the event horizon, and that disk can outshine every star in the galaxy around it combined. You might be wondering how astronomers can possibly know how far away something like this is, or how heavy its black hole is, when nobody's ever going to travel there to check. The distance comes from something called redshift. As the universe expands, light traveling toward us from a distant object gets stretched out along the way, shifted toward longer, redder wavelengths. And the amount of that stretching tells you how long the light has been traveling and how far it came from, which is how astronomers know TON 618's light left its source roughly 10.8 billion years ago. The mass is trickier, and it comes from watching how fast gas is swirling around the black hole in that accretion disk. Gas orbiting closer to a heavier black hole moves faster, and that speed shows up as a widening of specific chemical signatures in the object's spectrum of light, a widening caused by the same Doppler effect that makes an ambulance siren change pitch as it passes you. Measure that width carefully enough, and you can back-calculate the mass of something you'll never actually see up close. It's an indirect method, though, which is exactly why 2 separate studies, using slightly different techniques 15 years apart, arrived at 2 different answers for TON 618. This is where the numbers stop making intuitive sense. Estimates for the mass of the black hole powering TON 618 actually disagree among astronomers, and it's worth being upfront about that disagreement, rather than picking whichever number sounds scariest. An older analysis from 2004, based on the width of a particular emission line in the quasar's spectrum, put the mass at around 66 billion times the mass of our Sun, and that's the figure Guinness World Records lists as the record holder for the most massive black hole ever measured. A newer analysis from 2019, using improved methods, revised that estimate down to around 40.7 billion solar masses. so astronomers place TON 618 somewhere in a range between 40 and 66 billion solar masses, and honestly, either number is almost impossible to comprehend. For context, our own Milky Way's black hole, Sagittarius A star, comes in at about 4 million solar masses, and TON 618 outweighs it by a factor of somewhere between 10,000 and 16,000. Even more strikingly, either mass estimate for TON 618 is heavier than the combined mass of every single star in the entire Milky Way galaxy, combined. Not one black hole competing with one star, one black hole outweighing an entire galaxy's worth of stars. The light pouring out of TON 618 is just as absurd. Its absolute magnitude comes out to about -30.7, and its total radiative power is estimated at around 4 × 10 to the 40th power watts, translating to something like 140 trillion times the brightness of our Sun. That makes it, by some measurements, one of the brightest single objects ever detected in the observable universe, brighter than its entire host galaxy combined. So bright, in fact, that the galaxy surrounding it is essentially invisible from Earth, completely washed out by the glow of the black hole devouring its center. Fueling all of that light is gas falling into the black hole at speeds estimated up to 7,000 kilometers per second. Surrounding the whole system is a massive cloud of gas known as a Lyman alpha blob, stretching roughly 330,000 light-years across, more than twice the width of our entire Milky Way. Because TON 618 is so far beyond even a typical supermassive black hole, some astronomers have started using a new term for it, and objects like it: ultramassive black holes, a separate category entirely from the supermassive black holes that anchor most large galaxies, including our own. You'd think an object like TON 618 would be the most violent thing black holes are capable of producing, but there's something even more extreme, and it doesn't come from a black hole sitting still. It comes from two of them colliding. On September 14, 2015, at 09:50:45 Universal Time, twin detectors belonging to the Advanced LIGO Observatory in the United States picked up something no instrument on Earth had ever confirmed before: a gravitational wave, a literal ripple in the fabric of space-time itself, exactly as Einstein had predicted roughly 100 years earlier. To understand what that actually means, picture space-time not as an empty backdrop, but as something closer to a stretchy fabric, and picture two black holes spiraling into each other at the very end of their lives, whipping around one another so violently, at such a large fraction of the speed of light, that they physically shake that fabric, sending ripples outward in every direction, the same way a stone dropped in a pond sends ripples across the water's surface. Those ripples don't carry light or heat. They carry a stretching and squeezing of space itself, so small by the time they crossed 1.3 billion light-years to reach Earth, that they changed the length of LIGO's 4-kilometer detector arms by a fraction of the width of a single proton, and detecting that took building some of the most sensitive scientific instruments ever constructed by humanity. The signal, named GW150914, came from two black holes, one about 36 times the mass of our Sun, the other about 29 times, spiraling into each other and merging into a single black hole of about 62 solar masses. Now here's the detail that should genuinely unsettle you. If you do the math, 36 plus 29 should equal 65, but the black hole that came out the other end only weighed 62 solar masses. That missing 3 solar masses worth of matter wasn't destroyed, and it wasn't lost. It was converted directly into pure energy and blasted outward in a fraction of a second as gravitational waves, an event so powerful that for that brief instant, the raw power being released outshone, in terms of sheer energy, every star in the observable universe put together. This single detection confirmed one of the last untested predictions of Einstein's general theory of relativity, gave humanity the first direct proof that pairs of black holes exist and actually merge, and cracked open an entirely new way of observing the universe. LIGO physicist Kip Thorne, reflecting on what this meant going forward, said simply, "We are going to have a huge richness in gravitational wave signals." He was right, and it didn't take long to prove it. Less than 2 years later, on August 17, 2017, at 12:41:04 Universal Time, the same gravitational wave network caught something even more useful. Not two black holes this time, but two neutron stars, the ultra-dense collapsed cores left behind by dead stars, each weighing somewhere between 1 and 2 solar masses, spiraling into each other and colliding. This event, called GW 170817, became the first cosmic event ever detected in both gravitational waves and ordinary light, what astronomers call a multi-messenger observation. Just 1.7 seconds after the gravitational wave signal arrived, NASA's Fermi Gamma Ray Space Telescope caught a short burst of gamma rays coming from the exact same patch of sky, and less than 11 hours after that, ground-based telescopes around the world caught their first glimpse of visible light from the same source, a glowing object in a galaxy called NGC 4993 that astronomers named AT277 GFO. That glow is called a kilonova, a phenomenon theorists had predicted for years but had never actually observed until this moment, and it's powered by something extraordinary, the radioactive decay of brand new heavy elements, forged in real time in the wreckage of the collision through a process called rapid neutron capture. Spectroscopic analysis published in Nature confirmed that this single collision produced genuine quantities of gold, platinum, and uranium, meaning astronomers had, for the first time in human history, directly witnessed the birth site of the precious metals sitting in jewelry boxes on Earth right now. Dr. Joe Lyman of the University of Warwick put it about as plainly as it can be put. The heavy elements, he said, like the gold or platinum in jewelry, are the cinders, forged in the billion-degree remnants of a merging neutron star. The debris from that explosion was measured moving outward at roughly 100,000 kilometers per second, comparable to the escape velocity from the surface of a neutron star itself. And NASA's Chandra X-ray Observatory has continued tracking the aftermath for years since, watching the expanding debris slam into surrounding gas in what one research team described as something close to a sonic boom, echoing outward through space long after the initial collision. Colliding neutron stars are terrifying enough, but a single neutron star spinning on its own can be just as extreme, and one in particular holds a record that's almost hard to picture. Neutron stars themselves were purely theoretical for decades before anyone actually found one. Astronomers Walter Baade and Fritz Zwicky first proposed the idea back in 1934, suggesting that when a massive star explodes as a supernova, its crushed leftover core could collapse into an object made almost entirely of neutrons, packed to an unimaginable density. Nobody could confirm that idea existed in reality until 1967, when a Cambridge University graduate student named Jocelyn Bell Burnell, working under astronomer Anthony Hewish, spotted a strange, precisely repeating radio signal using a radio telescope she'd helped build with her own hands. That signal turned out to be the first confirmed pulsar, a spinning neutron star sweeping a beam of radiation past Earth, and it gave humanity direct proof that Baade and Zwicky had been right more than 30 years earlier. Deep inside a globular star cluster called Terzan 5, roughly 18,000 light-years away, sits one particular neutron star, one of the most extreme examples of a pulsar ever found, called PSR J1748-2446 AD, discovered by astronomer Jason Hessels and colleagues using radio telescopes in 2004 and 2005. It sends out a narrow, sweeping beam of radiation as it spins, the same way a lighthouse sweeps a beam of light across the ocean, and every time that beam crosses Earth, our instruments catch a pulse. Most pulsars rotate a few dozen to 100 times per second, which is already an almost incomprehensible speed for an object with real physical mass. PSR J1748-2446 AD rotates 716 times every single second, nearly 43,000 revolutions per minute, packed into an object less than 2 solar masses in weight, but crushed down into a radius of under 16 kilometers. Do the geometry on that, and its equator is physically moving at over 70,000 kilometers per second, roughly 24% of the speed of light. Theoretical physics suggests a neutron star could spin as fast as roughly 72,000 rotations per minute before centrifugal force would literally tear it apart, flinging its own material outward into space the way water flies off a spinning wheel. PSR J1748-2446 AD, at nearly 43,000 rotations per minute, is spinning at around 60% of that theoretical breaking point, meaning this object is, quite literally, close to ripping itself apart from its own rotational speed, and has been doing so continuously since long before humans existed to notice it. Let's shift away from black holes and colliding stars now, and towards something that can happen without warning, without any slow build-up, in less time than it takes you to blink. On December 27, 2004, astronomers detected what's been described as the brightest explosion recorded up to that point in human history. And it didn't come from a black hole, or even a supernova. It came from a magnetar, a specific and even rarer type of neutron star, one with a magnetic field so extraordinarily powerful that ordinary physics starts to strain trying to describe it. Strong enough that if a magnetar passed anywhere near Earth, it would theoretically be capable of wiping the data off every magnetic storage device on the planet from a distance of roughly 100,000 kilometers, purely from its magnetic field alone. To put that magnetic strength in perspective, an ordinary refrigerator magnet has a field of roughly 1/100th of a Tesla, and even the most powerful man-made magnets built in laboratories on Earth top out somewhere in the range of tens of Teslas. A magnetar's magnetic field is measured in the range of 10 to the 15th Gauss, which converts to somewhere around 100 billion Teslas, a number so far beyond anything producible by human technology that the comparison basically stops being useful past a certain point. It's simply a different category of magnetic field than anything else known to exist. This particular magnetar is called SGR 1800620, and it sits within our own galaxy, in the direction of the constellation Sagittarius. What happened that day is called a giant flare, and it lasted, in total, only a few hundred seconds, with the most violent part of it, the initial spike, lasting a mere 0.6 of a second. In that fraction of a second, the magnetar released roughly as much energy as our Sun puts out over about 250,000 years. Read that again if you need to, because it's not an exaggeration, it's the conclusion of researchers Mandaya and Balasis studying the event's effect on Earth's own magnetic field. Peer-reviewed analysis published in Nature placed the total energy of the flare at around 2 × 10 to the 46th power ergs, roughly 100 times more powerful than the only 2 previous giant magnetar flares ever recorded, one back in 1979, the other in 1998. The likely cause is a catastrophic cracking of the magnetar's crust combined with a violent reorganization of its magnetic field, essentially a starquake happening on an object already almost unimaginably extreme to begin with, a sudden fracture in a crust believed to be harder than steel, releasing energy that had been building for years in a magnetic field so twisted and compressed it simply couldn't hold itself together any longer. Multiple spacecraft caught the event, including Integral, Mars Odyssey, Wind, Swift, RxTE, and RESI, and the initial burst was so overwhelmingly bright that it actually overloaded and saturated the detectors on several of them, making the very peak of the flare difficult to measure precisely, simply because the instruments weren't built to withstand something that intense. And here's the detail that should really sit with you. This magnetar sits somewhere in the range of 30 to 50,000 light-years away, safely within our galaxy, but nowhere near us specifically, and the burst was still strong enough to physically disturb Earth's magnetic field, an effect researchers later confirmed using data from multiple satellites, including CHAMP, Ørsted, SAC-C, and Demeter. A magnetar, sitting tens of thousands of light-years away, rattled our planet's magnetic field measurably, in 0.2 of a second, without even trying, and it was, at the time, only the 3rd giant magnetar flare humanity had ever recorded. From an object that exploded in an instant, let's move to one that exploded and was still visible to human eyes despite traveling farther than almost anything the naked eye has ever detected. On March 19, 2008, at 0612 Universal Time, NASA's Swift satellite picked up a gamma-ray burst that would go down as one of the most extreme events ever measured. It's called GRB 080319b, and it came from the collapse of a massive star into a black hole, a process astronomers call a collapsar, where a dying star's core implodes so completely and so fast that it punches straight through into a black hole, while the rest of the star is still collapsing around it, driving twin jets of radiation out through the poles at nearly the speed of light. This particular collapse happened 7.5 billion light-years away, roughly halfway back to the Big Bang itself. What makes this particular burst legendary isn't just the distance, it's that for about 30 seconds, it was bright enough to see with the naked human eye, from the ground, without a telescope, despite traveling across more than half the observable universe to reach us. NASA described the scale of it plainly. For nearly a minute, this single star was as bright as 10 million galaxies. Swift recorded 4 separate bursts that day, and GRB 080319b was the second of them, and it remains, based on the observations gathered, the most luminous event ever recorded at optical and infrared wavelengths, with an extraordinarily high energy release in gamma rays as well. Ground-based telescopes, including a network called Raptor, caught the flash as it happened, and the Hubble Space Telescope later photographed the fading afterglow in early April of that year. Somewhere out there, right now, a star is likely doing exactly what that one did, collapsing into a black hole and briefly outshining 10 million galaxies, and we simply haven't caught it happening yet. Explosions like that one are things that happen to stars unimaginably far away, which makes them safe to admire from a distance. But there's a star close enough to us, one you could point to in the night sky tonight, that astronomers genuinely aren't sure hasn't already started dying. It's called Betelgeuse, the bright reddish star marking the shoulder of the constellation Orion, and it's a red supergiant, one of the largest and most luminous stars visible without a telescope, sitting somewhere between 500 and 650 light-years from Earth, depending on which measurement you trust. Betelgeuse has already burned through the hydrogen fuel in its core, and it's now working its way through progressively heavier elements, fusing helium into carbon, oxygen, neon, and magnesium. Once a star like this starts fusing iron, an explosion becomes essentially inevitable, because fusing iron into anything heavier doesn't release energy, it consumes it, and that robs the star of the outward pressure that was holding it up against its own crushing gravity, the same outward pressure that had been keeping it stable for millions of years. In late 2019, Betelgeuse did something that made headlines around the world. It started dimming dramatically, losing roughly 60% of its normal brightness by the time it hit its faintest point in early February of 2020. The dimmest the star had appeared in roughly 200 years of recorded observation. It actually dropped out of the list of the 20 brightest stars in the sky, and casual observers could see the change in the shape of Orion with their own eyes. Naturally, this sparked serious public speculation that Betelgeuse might be moments away, cosmically speaking, from going supernova. But research since then, including Hubble Space Telescope observations analyzed by a team led by Andrea Dupree, found a different explanation: a massive eruption from the star's own surface, a surface mass ejection that blew out roughly 400 billion times more material than a typical coronal mass ejection from our own sun. That material cooled as it expanded outward and condensed into a cloud of dust, which simply blocked some of the star's light from reaching us. It wasn't a warning sign of an imminent explosion, and Betelgeuse recovered its normal brightness later in 2020. But that doesn't mean the underlying question has actually gone away. A study published in 2023, examining Betelgeuse's pulsation patterns, concluded the star is in a late stage of its life, specifically late carbon burning, and called it a good candidate to be the next supernova visible in our galaxy. Some researchers have floated timelines as short as decades for when that might actually happen, though that remains genuinely disputed among astronomers, with other models suggesting it could still be tens of thousands of years away. What isn't disputed is that when Betelgeuse does eventually go, it will be perfectly safe for us, just spectacular, potentially shining as bright as the full moon and visible even in broad daylight for weeks, before fading and leaving behind either a neutron star or a black hole of its own. Not every terrifying object in space is an explosion or a black hole. Some of the most unsettling discoveries are things that simply shouldn't be there and don't behave the way we expect. On October 19, 2017, University of Hawaii astronomer Rob Werrick, using the Pan-STARRS 1 telescope on Maui, spotted a fast-moving object that would turn out to be the first confirmed visitor from outside our solar system ever recorded by humanity. It was later found in earlier images from October 14th as well, captured by the Catalina Sky Survey. Astronomers initially didn't know what to call it. It was first classified as a comet, then reclassified days later as a possible asteroid once no tail was visible, And finally, on November 6, 2017, the Minor Planet Center created an entirely new designation category just for this object, naming it 1I, with the I standing for interstellar, the first object of its kind ever confirmed. It received the name Oumuamua, a Hawaiian word that roughly translates to a messenger from afar arriving first. By the time it was spotted, Oumuamua had already swept past the Sun about a month earlier, on September 9th, coming within about a quarter of an astronomical unit and reaching speeds near 88 kilometers per second at its closest approach. Its orbital eccentricity was measured at roughly 1.2, a number so far beyond anything ever recorded for an object bound to our solar system that it proved, mathematically, this thing came from somewhere else entirely, passed through, and was never coming back. Physically, Oumuamua is strange in almost every way scientists could measure. It's estimated to be up to about a quarter-mile long, roughly 400 meters, and highly elongated, possibly 10 times longer than it is wide, an aspect ratio unlike any asteroid or comet ever observed within our own solar system. It showed no visible tail, nothing that would mark it as a typical comet, and yet its motion through space carried a very slight extra acceleration, the kind of nudge normally associated with a comet venting gas as it warms near a star. That contradiction, looking like a solid asteroid but moving like an active comet, is a big part of what made Oumuamua so difficult to classify. On top of that, it was tumbling chaotically rather than spinning smoothly, a sign it's likely a rigid, solid body rather than a loose pile of rubble. The leading scientific explanation, published in 2021 by Arizona State University astrophysicists Stephen Desch and Alan Jackson, is that Oumuamua is probably a fragment of a Pluto-like world from another solar system entirely, possibly ejected around 400 million years ago and slowly eroded during its long journey through interstellar space before it ever crossed paths with our Sun. That's the mainstream view, and most astronomers stand behind it. But it's worth mentioning, honestly, that a small number of scientists, most notably Harvard's Avi Loeb, raised the possibility that Oumuamua's odd acceleration and unusual shape could hint at something artificial, a light sail, rather than a natural object. That idea never gained broad acceptance in the scientific community, and the natural explanation remains the dominant one. But the fact that a serious astronomer even entertained the possibility tells you just how strange this object really was. NASA's Paul Chodas, who manages the Center for Near-Earth Object Studies, summed up the reaction well at the time. "What a fascinating discovery this is," he said. "It's a strange visitor from a faraway star system, shaped like nothing we've ever seen in our own solar system neighborhood." NASA estimates objects like Oumuamua actually pass through our solar system roughly once a year, quietly, undetected, simply because they're faint and our telescopes have only recently become sensitive enough to catch one. Since 2017, at least one more has been confirmed, Comet Borisov in 2019, meaning Oumuamua wasn't a one-time fluke. It was the first sign of something that's apparently been happening around us the whole time, unnoticed. If a visitor passing quietly through our solar system sounds unsettling, consider the objects that never had a solar system to begin with, or lost the one they had. In November of 2012, a team led by French astronomer Philippe Delorme, using the Canada-France-Hawaii telescope and later the European Southern Observatory's Very Large Telescope in Chile, announced the discovery of an object called CFBDSIR 2149, sitting about 100 light-years from our solar system. What made it remarkable wasn't just its distance, it was what it didn't have: a star. CFBDSIR 2149 is a free-floating planetary mass object, estimated at roughly 4 to 7 times the mass of Jupiter, drifting alone through interstellar space, with nothing orbiting and nothing to orbit. Because it isn't lit up by a nearby star, CFBDSIR 2149 can't be seen in ordinary visible light the way a planet normally would. It only shows up in infrared, glowing faintly from residual heat left over from its own formation, at an estimated temperature of around 400 degrees Celsius. Researchers place its age at somewhere between 50 and 120 million years, based on roughly a 90% probability that it belongs to a nearby group of young stars called the AB Doradus Moving Group, a cluster of about 30 stars believed to have formed together in the same stellar nursery. The leading idea is that CFBDSIR 2149 started out as a completely ordinary planet, orbiting a completely ordinary star somewhere, until a violent gravitational interaction, likely with another planet or a passing star, flung it out of its home system entirely, sending it drifting alone through the galaxy, with no sun to warm it, and no system to call home. There's an alternative explanation too, that it might not be a true planet at all, but a very small, dim brown dwarf, a failed star that never grew massive enough to ignite nuclear fusion, and researchers were upfront that more observation was needed to fully tell the difference. Philippe Delorme put the emotional weight of the discovery simply, "If this little object is a planet that has been ejected from its native system," he said, "it conjures up the striking image of orphaned worlds, drifting in the emptiness of space, and CFBDSIR 2149 might not even be rare." A later study using a technique called gravitational microlensing, published in the journal Nature, suggested our galaxy alone could contain hundreds of billions of starless, wandering worlds just like it, potentially more free-floating planets drifting through the Milky Way than there are stars to hold onto them. Wandering forever with no star to call home is one kind of nightmare. Being locked so close to a star that it's actively cooking you alive is another. And few worlds embody that better than Kelt 9b, announced in 2017 by a team led by astronomer Scott Gowdy of Ohio State University, located roughly 650 to 670 light-years away. Its host star, Kelt 9, is a blue A-type star roughly twice the mass, size, and temperature of our own Sun, with a surface temperature around 9,900 degrees Celsius. Hot enough that if you could see it with your naked eye, it would look bright blue in the sky, rather than the warm yellow-orange of our own Sun. Kelt 9b itself, nearly 3 times the mass of Jupiter, orbits that furnace at a distance of just 0.035 astronomical units, more than 30 times closer to its star than Earth is to the Sun, completing an entire orbit in only about a day and a half. The result is a planet with a dayside temperature of roughly 7,800 degrees Fahrenheit, hotter than many actual stars, and only about 1,000 degrees Celsius cooler than the surface of our own Sun. Kelt 9b is tidally locked, meaning the same face permanently points toward its star, trapped in eternal blistering day, while the opposite hemisphere sits in permanent night, with heat and gas constantly flowing between the two sides, trying and failing to even things out. In 2020, a team led by Megan Mansfield of the University of Chicago, using NASA's Spitzer Space Telescope, found something almost unbelievable. The heat on the day side is so extreme that hydrogen molecules in the atmosphere are being physically torn apart into individual atoms, unable to hold themselves together, only managing to reform once they've circulated around to the cooler night side. This kind of planet, Mansfield said, is so extreme in temperature, it is a bit separate from a lot of other exoplanets. And the planet isn't just cooking, it's actively dying from it. Radiation from the star is stripping away its atmosphere at an estimated rate of somewhere between 10 billion and 10 trillion grams of gas every single second, and researchers estimate that within roughly 300 million years, much of Kelt 9b could simply evaporate away into space entirely, boiled off by its own sun. We're going to end this journey with something a little different, not an explosion, not a scorching hot Jupiter being boiled alive, but a slow-motion death happening in real time, close enough and clear enough that scientists have actually watched it unfold, piece by piece. It's a planet called WASP-12b, discovered in 2008 by the Super-WASP Transit Survey, orbiting a yellow, sun-like star roughly 600 to 1,400 light-years away in the constellation Auriga, depending on which measurement you go by. WASP-12b is what astronomers call a hot Jupiter, a gas giant that, instead of orbiting far from its star the way Jupiter does in our own solar system, orbits so close that it completes an entire year in about 1 Earth day, 1.1 days to be exact. It sits only around 2 to 3.5 million kilometers from its star, a sliver of the distance separating Earth from our own Sun, and as a result, it's absolutely cooking, with surface temperatures estimated somewhere between 2,200 and 2,800 degrees Fahrenheit. The gravitational tidal forces at that distance are so extreme they've physically distorted the planet's shape. stretching it into something closer to an egg or a football than a sphere, nearly twice the radius of Jupiter and about 40% more massive. Here's where it gets genuinely disturbing. On May 20, 2010, using Hubble's Cosmic Origins spectrograph, a team led by Carol Haswell of the Open University in the United Kingdom directly observed material being stripped away from WASP-12b's atmosphere and pulled into a swirling disk being consumed by the star itself, complete with heavier elements like aluminum, tin, and manganese detected in that escaping material. It was, at the time, the clearest direct observation ever made of a star actively eating a planet. Haswell described what they found plainly. "We see a huge cloud of material around the planet, which is escaping and will be captured by the star," she said. "We have identified chemical elements never before seen on planets outside our own solar system." When this was first observed in 2010, researchers estimated WASP-12b had roughly 10 million years left before it would be completely consumed. But more recent measurements, tracking the planet's orbit using data that includes NASA's Spitzer Space Telescope, found something more urgent: that the planet's orbit is measurably shrinking year over year, and the collision is now expected far sooner than originally thought, somewhere around 3 million years from now. Given that the star itself is estimated to be only about 3 billion years old, that means this particular planet is going to die shockingly young, cosmically speaking, and we happen to be alive at the exact moment in its multi-million-year story where we can actually watch it happen. So there they are, 13 of the most extreme, most genuinely terrifying objects and events astronomers have ever confirmed exist. A black hole close enough to call a neighbor that once flung an entire star out of the galaxy, and elsewhere, one of its cousins caught in the act of tearing a star apart limb from limb. A black hole so massive it outweighs every star in the Milky Way combined. Two black holes colliding so violently they briefly outshone the entire visible universe, not in light, but in raw energy, through ripples in space-time itself, and not long after, two neutron stars colliding and forging the gold and platinum sitting in jewelry boxes on Earth right now. A neutron star spinning so fast it's a hair's breadth from tearing itself apart from its own rotation. A magnetar that shook Earth's magnetic field from tens of thousands of light-years away in 0.2 of a second. A dying star that briefly outshone 10 million galaxies. A nearby giant star, close enough to see with your own eyes tonight, one astronomers genuinely can't rule out, has already started its final countdown. A silent visitor from another solar system that passed through our own and vanished again forever. A wandering, starless planet drifting alone through the dark, with nothing to call home. A planet so close to its star that its own atmosphere is being torn apart atom by atom. And a planet, right now, in real time, being slowly devoured by the very star that gave it life. Space doesn't need monsters or aliens dreamed up in a writer's room to be terrifying. The universe we've actually measured, the one backed by data, telescopes, and peer-reviewed research, is more than unsettling enough on its own. If this kind of deep dive into the extremes of the cosmos is something you want more of, make sure you're subscribed, because there is a great deal more of the universe left to be afraid of.